Okay, our next topic is something called a Wheatstone bridge. But I'll teach you meter bridge, because if you don't know Wheatstone bridge is actually a concept, an arrangement of four resistances. Why do we use that? That is used in an appliance called meter bridge. It's a laboratory device in which you can find the resistance of an unknown resistance. As of now, just imagine that one. Given an unknown resistance, any wire, and you want to find its resistance, so we can find it in the lab using an apparatus called, or a laboratory device called meter bridge. Meter bridge works on the principle of Wheatstone bridge. So let's first see what is a Wheatstone bridge. Wheatstone bridge is a combination of four resistances. Very easy, and just needs some little bit of common sense. Okay, it's a combination of four resistances, and while drawing, we draw it in a rhombus pattern. We'll draw it in a rhombus pattern. So exactly like a rhombus, two resistances on the top arm and two resistances on the bottom arm. Right. And this bridge will be powered by an external cell. This bridge will be powered by an external cell. This is what a Wheatstone bridge looks like. This is an arrangement of Wheatstone bridge. Four resistances in a rhombus pattern, in which two resistances will be on the top arm, two below. So we call them as, say, PQ. Typically, we have learned this way: R1, R2, whatever you say, PQ, RS. Right. So we see one junction A out here, and we see another junction B. First, understand Wheatstone bridge, and meter bridge becomes very easy to understand. And then what we do, we trace the path of the current. So this is the circuit current, and the circuit current, say I, has now entered on the top arm. This is, say, I1, sorry, and this is the top arm. So this current is I1, and this current is I2. Is this much understood, beta? Now I1 keeps on going, doesn't find any other road, so the current on this arm will also be I1, and this current is also I1. Similarly, this is also I2, and this is also I2. Is this understood? So from here, applying Kirchhoff's current law, we can say the I current entering divides into I1 plus I2. Is this understood or not? Now in this Wheatstone bridge, what we do, so this is, say, AB, and then let's say we have a node C and a node D. Between node C and node D, we have made another connection, and what we have done here, we have placed a galvanometer out here. Galvanometer. Now you should know what is a galvanometer. A galvanometer is a device which is used to tell me whether any current is there in a circuit, and if the current is there in a circuit, which side is the current flowing. A galvanometer is a small device. Now you may say, sir, why are you not using an ammeter? An ammeter tells me the strength of the current. Galvanometer is very sensitive. It will just tell you whether there is any current or not, and if the current is there, in which direction. So a galvanometer as a device will have a central zero, which means, and that central zero of a galvanometer, so a galvanometer will be a device like this, whose zero will be on this side. This side measures plus ampere, this is minus current. So my pointer will be like this, and this is known as null deflection. What do we call it? Null deflection. Null deflection means galvanometer is not sensing any current. It's like that the father sent for exorcism, and it's his rosary, and it is not sensing any spirit out there, so no current. Now in Wheatstone bridge, we have a condition called the balanced Wheatstone bridge. Balanced Wheatstone bridge. Now what do we mean by a balanced Wheatstone bridge? A balanced Wheatstone bridge is one in which the galvanometer will show null deflection. It will show what, beta? Null deflection. Do you agree? That means there should actually, I have created another junction out here now, C. So there should be one more current here called IG. Do you agree or not? And this IG will be reading as 0. This is called the balance of the Wheatstone bridge. There is no current flowing in this part. Sir, how did you do that? How did you do that? By some twisting and tweaking these resistances, I have created such value that this galvanometer shows 0 deflection. And when the galvanometer shows a 0 deflection, 1 meter. Okay. When the galvanometer shows a 0 deflection, it actually means that no current flows through the galvanometer. Is this understood? Fine. So without this condition, you cannot arrive at the condition of balanced Wheatstone bridge. So what I'm going to derive now is when a Wheatstone bridge is balanced, what is the condition that we have? What is the condition we have? Shall we? Okay. So what we do, we apply Kirchhoff's law and we take a loop. Let's take the loop. Which loop will we take? We'll take ACDA. ACDA loop. Fine. ACDA loop. Now in ACDA loop, I'm going through this side. So the potential will drop. So it's a negative I1 into P. Do you agree? Negative I1 P. Look here. I'm not writing each branch separate. I hope you'll be able to understand. Negative I1 P. Come down here. IG is 0. Galvanometer does not have any internal resistance. Any current measuring device cannot have any resistance at all. A meter has no resistance. And this is super sensitive. So it cannot have any resistance. Agreed? So now you're coming this way. You're going against the current. So this potential is building up on you. So this potential will be how much, beta? Plus of I2Q. This should be equal to 0. And if I write it properly, can I write I1P is equal to I2Q? Can I write this? Balanced Wheatstone bridge, and you have to write that in this condition IG is equal to 0. That is, no current flows through G. Clear? Then let's take the next loop. Our next loop is what, beta? Our next loop is CBDC. CBDC. This loop. Chale? So if you look at CB, look here. It's a reducing potential. Current is along your side. So it's a I1R. It's a negative I1R. It will be a negative one because you're going along the current. And then you are obstructing the current. So it's a build up. So it will be plus I2S equal to 0. This gives me what, beta? This gives me I1. Yeah. Can I just, yeah, not an issue. You can take this also. So I1 into R equals to how much, beta? I2 into S. These are my two equations. Equation 1, equation 2. Is it okay so far? Now you just do equation 1 divided by equation 2. What do you get? You get a P upon R, okay, is equal to Q upon S. This is the condition of balance of a Wheatstone bridge. And why I wrote it? Because from my school days, we have been familiarized with this formula, P by Q equal to R by S. What does this mean? It means in a combination of a Wheatstone bridge, if you set it up in such a manner that you can make the IG 0, if 3 resistances are known, the 4th resistance can be found out using this formula. And always remember, it's always like this. See, P by Q, it will come like this, is equal to R by S. So let me repeat it once again. What is a Wheatstone bridge? A Wheatstone bridge is a combination of 4 resistances arranged in the pattern as shown in the diagram. Got it? And the two vertices A and B, or the two nodes A and B, are fed with a cell whose voltage is B. A current I enters it and splits up into I1 and I2. And then C and D are short. This C and D, you short this C and D. You have shot it through a galvanometer, and the balance condition is when no current flows through the galvanometer. That is very, very important. And that we will see. If you're why I dislike the way it is taught. If you are taught this and you're not taught meter bridge, you will not understand how you make this zero. Now we will see in real life how you make it zero. Once you have made it zero, you attain something called balance. And at that balance, this condition will be there. Children, one thing is for sure. So suppose you get a 1 mark question. A galvanometer here is showing a deflection of say 0.01 ampere. Can you use this equation? Not at all. Not at all. This equation is valid only when the current through the galvanometer is zero. Null deflection, balance Wheatstone bridge. Understood? Your course ends here, but we will see how a meter bridge works and how in lab you actually set this. Is this drawing is in your mind? Now we will see the same drawing but in a different setup. So you have to put those two together. Shall we? Let's see. Okay. So what is a meter bridge? Okay. A meter bridge will actually have, I'm exactly drawing how a meter bridge looks like. Okay. A meter bridge is a wooden block. In labs, it will be a wooden block like this. Like this. There's a wooden block like this. In this wooden block, there will be copper plates. Copper plates like this. There will be copper plates. So many meter bridges we have drawn. So this is 1. Two. And this is exactly like a wooden board, like a chopping board. Got it? So meter bridge. And you will try to figure how that particular drawing is met here. Okay. On this copper board, there will be knobs. Knob. Got it? This knob will be connected cell. It's connected. I didn't get you. Come again. Copper plates, strips of copper. So it is in this manner, right? Then I'll have a knob out here, one knob out here, one knob out here, and I'll draw a drawing also. Don't worry, it will be very interesting. One knob out. Okay, right. So here, what I will do, children, I am given an unknown wire. My lab sir has given me an unknown wire and he has asked me that you find its resistance. So I have taken my unknown wire and I have connected here. I'm supposed to find the resistance. Got it? Then what will I do? From the lab, I will pick up a known resistance. I'll pick up a known resistance. This is a known resistance. Say whatever ohms it is, I'll pick this up. This resistance is known to me. Perfect. And then the most interesting, why it is called a meter bridge, I have a exactly 1 meter wire which is connected out here. How long? 1 meter. So what you will have here apart from this 1 meter wire is which color do I use? Okay, pink. So here we will have something called pink color, a graduated wooden ruler, out here. So this ruler will be marked in centimeters. Got it? So it starts from 0 and it ends at 100 centimeters. Is this understood? And this wire is exactly 1 meter long. That's why this is known as a meter bridge. Meter bridge. Now let's see what we have done. Okay. Let's see what we have done. So let me draw the Wheatstone bridge setup. How did I name it, children? I named this as A, this is B, this is C, this is D, this is P, And this was Q, this was R, this was S. Now see how I'm naming it, okay? My cell comes to A, so this point is A. No, don't, that I don't like that. You pay attention here. This is not there in the syllabus. My cell comes to A, so it has come to A. Agreed? From A, I have a resistance P. This is a resistance P. I don't know that. Then there is a resistance R, which I know. Very good. I know that resistance. Sir, what about Q and S? What about Q and S? And sir, you also used to have one galvanometer out here, G, and used to ensure that Ig is equal to 0. Right? So what we will do here, from here, we will be connecting another wire, and this wire is coming out from here, okay? Just otherwise it will damage the drawing. Have you understood? Okay, let me say it's coming out from here, and then we will connect one galvanometer out here. All right, so this is A, B, and I can say this as C now. Is a copper plate. If this is C, this is also C, this is also C, no question. This is my galvanometer, and from the galvanometer there is a device available in lab which looks like a stylus, has got a knife edge, and I call this as jockey. This is called a jockey, and the jockey is connected out here. Fine. Cell turned on, galvanometer will be showing some reading, and you are free to slide your jockey. As you bring the jockey this side, you will see the galvanometer maybe on that side or this side. If you take it this side, it will be going on opposite, which means somewhere in this wire, did you understand what I'm saying? Suppose if you keep the jockey on the extreme left, you may see the galvanometer either on the extreme left or either on the extreme right. Say the galvanometer is on the extreme right. Say, when you take the jockey can be, the jockey is with a wire. Your wish where you put the jockey. When you put the jockey out here, you will see exactly opposite deflection. So one thing strikes that as I keep on moving it from here, the jockey should come back. Sorry, the galvanometer should come back. And some point the galvanometer should show null deflection. That means no current is flowing through. No current is flowing through CD. Are we fine? At that time, let this length of the wire be L. Then how much is the length of this much of the wire? 100 minus L. Material is known to me. Cross section is known to me. Resistivity is known to me. What is the length of this? The resistance, this would be my resistance Q, whose resistance value will be rho L upon A. This much is also a resistance, na? And this much will be a resistance which will be S, which will be equal to, again, same material wire, 100 minus L upon A. Because the wire has not changed. Right? What is the condition you obtained? P by Q is equal to R by S. Let's shift this ratio. P by R is equal to Q by S. I can write that also. What is the value of Q? The value of Q is ultimately rho L, and rho L will get disconnected. Do you agree or not? So a Q by S can be written as L by 100 minus L. Right? And this is how we do it in a lab. So what we will do, we will put our unknown wire here and a known resistance out here. And then we will slowly slide the jockey and bring at a null point. Very interesting, and an experiment where you get full marks. Meter bridge Anna means kiss your fortune. You're very, very lucky. This experiment cannot go wrong. And then you put your jockey out here. At that moment, galvanometer is 0. You just note what is the reading here. You need not note it because this is 100 minus this. Next set of values, what we will do? So here we keep a resistance box. In lab, we call this as a resistance box. So in a resistance box, there will be many resistances. You just keep on opening the plug keys. So you change this value. For a different set of value, again, somewhere else, you will get your balance point. And this point is known as the balance point. You will get a balance point somewhere else. Again, you do P by Q, R by S, and you keep on finding out P. So say they will actually put a sticker on P. They will not tell you what is P. Say P was 1 ohm. On one set of experiment, you will get 0.99 ohm, 1.01 ohm, 1.03 ohm, 0.101 ohm. Like this you will get. Take the average and give your answers before you're done with your lab. Did you understand how Wheatstone bridge is applied? Meter bridge works on the principle of Wheatstone bridge. And in meter bridge, we can always have this G is going to have some value. In order to bring G as 0, what we will do, we will bring it to a null point. And at null point, this is a Wheatstone bridge. Now just apply, you ask yourself the question, where is A? A is here. From A, there is a resistance P. It goes to C, then C to, then it goes to B. So this is B, right? No, this is not B, because B is after the resistance. So this is B. If this is B, this is also B. And then you get your resistance, then you get this much value. So your jockey will be actually touching here, not the scale. So this becomes your S, this becomes your Q. Jockey is like a slider. You made a Wheatstone bridge, na? No. A jockey is just a pen like this. Back there will be a terminal where we'll turn the wire, and on the other side, have you seen a small chisel? A jockey is just like a chisel. It won't be pointed, it will be like a screwdriver, flat. So your job is to keep on touching the jockey here. You will see no null deflection. Within 2 minutes, you will be able to balance it. Because if you move this side, the galvanometer will move on one side. If you move the other way, it moves opposite. You have to bring the galvanometer exactly at a steady still null. So wherever it is null, keep the jockey touch there. Wherever you touch the jockey, the wooden scale will be there. So you know what is the reading. So if the reading from here to here is 30, the reading from the left balance reading is 70. Similarly, there is another one device called potentiometer. Potentiometer was also earlier in grade 12. Similar device, which is used to compare the value of EMF of two cells, strength of EMF of two cells. If you don't study this and you study this, you don't develop the love for this. The love for this gets developed when you see this, and this can be done. In fact, hardly it costs anything. Some 400-500 you can keep at home and keep on doing resistance tests. Done? Any questions on Wheatstone bridge? Have you understood like how we derived this thing? This derivation sometimes comes, and if it comes, it's a full marks. Okay, so we'll now take up problems from your book. And your favorite problem, you had that cube problem. You used to say how to solve that cube problem. So we'll see the cube problem also. Okay, chalo. Let's see the cube problem. The cube problem is actually easy. Unnecessarily, you all are confusing, but there's a technique to do that problem. So once you understand. Okay. Can you tell me in this cube problem, this is vertex A, I think, A. This is C, I think, if not wrong. C. You have the textbook? This is A, this is C. Then we have one as C dash. I think there's a D, there's a B.
C dash is on top.
The C dash is on top, right? The C is at the bottom. Okay, and then this one is
B dash. Oh, that's
B. And then this is
B dash.
D dash. This is
B dash.
A dash. And what about this? B dash, right? And I think there is a cell which is connected from between A and C, if I'm not wrong, A and C dash. Okay, ठीक है, चलो. So I think Neha, you can hear me now. Yes. Yeah, okay. This one has expired. Okay, what I was saying, that this is a symmetric figure, and if the figure is symmetric, then the three currents which are entering at the vertex A can be taken as I. Have you understood? Sir, why didn't you take this as I? If I take this as I, there will be I by 3, I by 3, I by 3, which makes my calculation go a little bit more complicated. Fine. Now, I current is going in this direction, and so what will be the potential drop out here? If you see the potential, if you see the current, this is I. So the potential drop will be, let's say, I into 1. So it's only I. Okay. If you see out here, then we have got two resistors. Both resistors are connected in series. Both resistors are connected in series. Do you get it? Each is 1 ohm, 1 ohm. And I current is only flowing. If you see, I has come here, and then this current becomes what? Let's say this current becomes I1, and this current becomes I2. This is I2 now. Clear? I becomes I1, I2. Now tell me one thing. This is a series connection. This is a series connection with two equivalent resistance of 1 ohm each. If the resistance was 1 ohm, what is the voltage? Voltage is always equal to IR. If your current is I and your resistance is 1 ohm, then your voltage is equal to I. So here the drop will be I. But here total voltage will be distributed across these two resistances because they are in series. Which one?
Distance.
As of now, just concentrate on AB. In AB, just concentrate AB. I current is coming. There is a resistor 1 ohm out here. What is the drop out here? I into 1. Correct? The current goes here. This is a junction. Do you agree or not? Then the current has split into I1 and I2. I am still concentrating on I2. My I2 goes here. My I2 will be here also. No questions arise. And here also it's a series. The same current will be flowing. Current is not getting any more path to get out. Now it will go into CD. So we will hold CD as of now. So you're correct. It will go to get into CD. So I'm considering only up till C. I current is going on. Fine. Then let's see here. It's I. I will again split up into two nodes out here. The same current goes and will split up into two values. They are all symmetric. They're all symmetric. Now that's what if you look at the current, it is going up in two directions. So I'm saying my current becomes, instead of writing 1 minute, 1 minute. Instead of writing I1 and I2, I'm saying my current I goes from here. It splits up into two directions. Exactly same resistances are there, and by symmetry, this current will be I by 2, and this current here also will be I by 2. Do you agree or not? Okay, let's see here. I current is going. Current becomes how much? I by 2. I by 2. Agreed? I by 2 current come again, combine here and become what? I current is flowing. Now let's see here. I by 2 current is going. I by 2, and let's see here what is happening. I current becomes I by 2. So let's see. I by 2 meet at B dash will become how much? I. Very interesting. See, and here what is happening? Between A and D dash, I by 2 is going. Between D and D dash, I by 2 is going. So this current becomes how much? I. Ultimately, all three I's are pairing up, and the overall circuit current becomes 3I. Clear? This is the difficult part which you have already done. Now, shall we apply what is called Kirchhoff's loop rule? So let's take a loop now, and let our loop be, let's take a loop. Our loop is A, will involve the cell A, B, C, then beta C dash, and then घूम फिर के A. A, B, C, C dash, A. Right? So let's start. Come on, we'll do like the other day. AB arm. AB arm, what do you see? You're going along with I current. How much is your potential? Negative I. Okay? Then you are going this way. Again, you are going along in BC. BC, it will be negative I by 2. Very good. Then you are going CC dash. CC dash, it is negative I. Right? Then what happens? Then you come to C dash A. We have tallied. C dash A, we are building up potential. We are building up potential. So this is positive 10 volt. Agreed? All these sigma should be equal to how much? 0. Right? So let's do it. So I becomes how much beta? 2I. 2 and 2.5. This is 2 plus 2.5. So negative 5 by 2I plus 10 is equal to 0. Did you understand 5 by 2 I have written? 2 plus half. 2 plus half is 5 by 2. Right. So I can now write 5 by 2I is equal to 10. So 5 2s are 10. I is equal to how much? 4 ampere. If I is 4 ampere, your overall circuit resistance is how much? 10 by 12. 2 5s are 10, 2 6. So R is equal to 0.68s are 48, 20, 6 3s are 18, 8.33 bar. Ohms. We think it is difficult. It is not difficult. It is an easy question. Did you understand, Arjun? That 5 by 2 you understood? I think it has it tallied with book? 5 by 2. Sure. Shall we do one more? We have time. We have one more on the loop. That trapezoidal triangular one. How does it look like? Okay, this. Oh, there's a cell also. 1 minute. Can I change? Okay. Let's see the next one. A, B, C, D, A. Determine the current in each branch of the network. In each branch of the network. Which one, Bitu? Oh, that cell? Good. That is a 10 volt cell. So you have to determine the current in each. So what was the rule we said? You can take out current from each any cell that you feel like. So where do you want the current to be taken out from? 10 volts or 5 volts? Always I said higher is the potential, take it out from there. So the calculation will become, otherwise unnecessarily you will land up with a negative. Okay. So let's say our current is coming out from here. So what do I call this current as? I1. Okay. I1 current is going, and I1 current has, now how do you then say, let's say, what do we call this current as? Don't make three variables. Okay. Let's call this current as I2. If this current is I2, then this current should be what? Addition of these two currents. So what should we call this current as? I2 minus I1. I2 minus I1 plus I1 gives you I2. Could you understand this? There's a junction rule that we have applied. Then how much current is coming here? Here is I2 current is coming here. How much current is coming here? I1 current is. How much current is coming here? I2 minus I1 current is coming. Now how do you do the next one? There has to be a third current also that we have to produce out here. All right. So if we take this current as, say, I3, this, right? So this current should be the sum of, this current should be I3 plus I2 minus I1. Did you understand? These two currents addition should be this. This current has split up into these two currents, right? Then how much is this current? I3 minus I1. What is this current? I3 minus I1. Both have merged and finally they are giving you I2 plus I3 minus I1. So I2 plus I3 minus I1. Look. How our speculations is correct. I2 plus I3 plus. Whatever current we got here is the same current. Means our distribution is absolutely correct.